Okay, and equipped with this, we can finally look at graph cuts, which Kolmogorov invented in his PhD thesis around 2000. And in much of the following, I'm referring to this paper here, which is suitably called "What Energy Functions Can Be Minimized via Graph Cuts." And this paper starts with two definitions, namely, what is graph representable? So which energy functions can be represented by a graph so that finding the minimum cut in the graph amounts to solving the original problem. And the paper builds on this theorem by Hammer that submodular quadratic pseudo-Boolean functions are graph representable. So graph representable. Some function e of binary variables x is graph representable if there exists a graph with a number of vertices such that for any state of these binary variables x, this energy is equal to the cost of a minimum ST cut plus a constant. By computing the minimum on this graph. And well, polynomial is not good enough for images when you deal with millions of random variables. So what you need is a really small prefactor. And this is one of the merits of Kolmogorov's thesis, to have offered an algorithm that is super efficient for grid-shaped graphical models. You also further need the theorem by Hammer, namely that submodular quadratic pseudo-Boolean functions are graph representable. So Hammer already in the 60s showed how to construct graphs on which you could do a max flow computation that would give you the globally optimal energy optimum for a quadratic pseudo-Boolean function. There's also an additivity theorem which says that it's enough, or that the whole thing is additive over all contributions, so it's enough to just look at a single pair to understand what's going on in this entire quadratic pseudo-Boolean function. because we have only cliques of size 2, we need to consider only 2 random variables that are in a common clique. So let's look at this graph construction. And we start by the unary or the single side terms. Psi I of xi, and we can construct a tiny graph comprising this vertex vi that has 2 capacitated edges. There's one edge with psi I of 1 and one edge with psi I of 0. So I used the convention that xi is considered to be 0 if it's connected with the source and 1 if it's connected with the sink. So S corresponds to label 0 and T corresponds to label 1. And if, for example, I cut here, then the cost of this cut, there's just a single edge from source to sink traversing this cut. So what this cut does is it assigns Vi to the source, which in our convention here means that xi equals 0, and it incurs a cost of, well, the capacity of this edge, and the capacity of this edge here was psi I of 0. That is assuming that these psi's are non-negative numbers.
So psi before gave us the energy of a particular state.
Yes.
Now it gives us the capacity.
Exactly. So psi before was used to give energy, and now the energy of an assignment, and now it corresponds to the capacity of n edge. So this cut, the cut down here, gives me a cost of psi I of 0. If I take this cut here, this incurs a cost of psi I of 1. And of course, as the name says, the max flow or minimum ST cut algorithm will find the cheaper of the 2 cuts. So if psi I0 was lower than psi I1, then the lower or the bottom of the 2 cuts would be performed. Okay, and then I have a similar construction for my vertex J. So this is psi j of 1, this capacity here, and that capacity is psi j of 0. And now these 2 graphs can be combined into a single one. So let me write plus, because we have a summation in our energy function. So here's my overall graph. for the unaries of I and j only. Now this graph can be simplified a little bit. It said that the equivalence has to hold true only up to some constant. So epsilon of x is a constant plus, if I'm writing down only the unary terms now, it would be that. And if, for example, let's say if psi j of 1 is larger than psi j of 0, then I can subtract this quantity from both involved edges and obtain a graph with updated capacities. So this would be psi j of 1 minus psi j of 0. I'm only concentrating on node j now, so I'm omitting node I. And here we have an edge of capacity 0. Now if I've updated these capacities, I know that I should add some value to my energy. So I would say that in this case the energy of x is psi j 0 plus the min cut value. If previously I had a 0 here. Because if I now cut here, the cost of this cut is 0, but I wanted to represent the same energy, so I have to update the constant in my energy function. Well, and this construction here works okay if psi I of 1 is greater than psi j 0, because capacities must be non-negative. If it was the other way around, psi j of 1 was smaller than psi j of 0, then I could construct this other simplified graph where I would retain only this edge here. X would now be psi j of 1 plus the min cut value. What would prevent us from?
The question is, what would prevent us from just doing that iteratively to all of our connections basically reduced from our graph?
We've only talked about the unary terms now. We still need the pairwise terms. So if I had no pairwise terms, then I would assign each pixel, then I wouldn't need the, this algorithm in the first place. Then I would assign each pixel to foreground or background depending on what's more likely. Okay? So that would be thresholding. So here we've looked at the unary or single side terms. And after the break, we can look at the pairwise terms. And construction for the binary or pairwise terms will become a little more involved after the break. Not talks, but terms. All right, so we finally have all the ingredients, can bring everything together for the grand graph construction. We're now looking only at the pairwise term. So I'm saying that the energy of X is some constant, which in the last few hours we had omitted because it's irrelevant for finding the most likely state, or that of lowest energy. It's irrelevant for the map problem. Plus, omitting the unary terms, we're looking at pairs of vertices I and j. It's totally illegible. Pairs of vertices I and j in the edge set. Zero, zero. If I'm now using this notation that we saw for the pseudo-Boolean functions, there we go. And this is A, B, C, and D. So I can compile these entries in a table. Where I can take values, or xi can take values 0 or 1, xj can take values 0 or 1. So these abbreviations will help us. And I now want to express this energy in terms of a graph. So I have a source node corresponding to label 0. I have a sink node corresponding to label 1. And then I have two vertices, Vi and Vj. That are in the edge set, and then I want to find the capacities that I should choose. So I'm calling these K, M, and P. I want to find the capacities that I should choose so that the ST min cut will give me the value of the energy up to some constant. Now I can have 4 different cuts that will give me 4 different conditions. So let's say this is cut number 1. This would be cut number 2. I can already give these conditions. So the first cut tells me it will have a value of K, because that's the capacity of the only edge crossing this cut in the right direction. And I want this K plus some constant offset to give me the correct energy value. So if I use this cut number 1, then both Vi and Vj will be assigned label 1. So this is CI11 psi ij, excuse me. I'm writing them down here explicitly. So this should be D. Just as a reminder, D was the abbreviation here for psi ij of 1, 1. Okay, because cutting here in this position number 1 should cost me D according to the original energy function. Now I can instead make this cut number 2, which has one edge pointing across the cut in the right direction. And if I make this cut number 2, then this node Vi will be assigned to class 0 and Vj will be assigned to class 1. So this should incur the cost of B, where B was shorthand for psi ij of 0, 1. I can have a cut 3. Which gives me another condition, namely that P plus delta should be A. Cut number 3 assigns vertices I and j to class 0, so that corresponds to A. And finally, there's just one possible cut left. It cuts both K and P. M does not add into the count because the edge M goes in the wrong direction. So we're only counting edges that go from source to sink. So this edge here cuts crosses the cut in the correct direction, but this one goes in the wrong direction, so it's not counted, and this one goes in the correct direction. So K plus P plus delta should be C, which is shorthand for psi ij of 1 and 0. This is delta. It's the same offset that I had in all equations, the offset for the energy. Thanks for asking. So the minimum cut, if we go back to the definition, here the cut set is the set of edges I and j, where I has to be in the source set and j has to be in the sink set. And here V, according to this cut 4, let's make it a little bit longer, Vi is in the set of the sink and Vj is in the set of the source. This is why it's not counted. And the theorem, the max flow min cut theorem, only holds for the min cut as defined here. So if we, looking from a distance, we have 4 knowns. So these values psi are given. We have designed them by hand or we've learned them somehow. And we have 4 unknowns. So we have the unknowns are K, M, P, and delta. And we have 4 equations, so we can determine the value of these 4 unknowns, or we can express the capacities in terms of the original potentials. So aim is to express the capacity P and the offset delta in terms of the potentials. So the fourth equation involves K and P. So I can put equation 1 and equation 3 into equation 4 by saying that so K is given by D minus delta and P is given by, according to equation 3, A minus delta plus delta is C, and overall this gives me a minus delta, which I can bring on the other side. So delta becomes A minus C plus D. So A, B, C, D were just shortcuts or shorthands for my potentials. So I already have the first equation here that tells me what delta should look like in terms of, so delta was known, and these here were given. Then in addition, I have non-negativity constraints, non-negative capacities, non-negativity of the capacities. So for example, K, which according to equation 1 is D minus delta, should be no less than 0. And similarly M, which is B minus delta, should be no less than 0. And P, which is A minus delta, according to, what was it, equation 3, should be no less than 0. And I can now insert what has been found for delta in all of these equations, and that gives me the following. So D minus D, so that cancels. Overall I obtain that C minus A is non-negative. Here I obtain that B plus C minus A minus D is non-negative, and here I obtain that D minus C, no, C minus D is non-negative. Now one of these equations is fundamental and the others are just consequences of this arbitrary graph construction that I used. Because I used a sparse graph here with 3 edges, but I could have used other edges. So this equality here, or inequality, is fundamental, whereas the other two are just consequences of the particular graph I showed. And fundamental means this is the celebrated submodularity condition. Or to write it out in its full glory, remembering what B and C and so on were. B and C were the off-diagonal terms. So this is phi ij, what was B? 1 plus psi ij of 1, 0. they must be larger than a plus d, which was psi ij of 0, 0 plus psi ij of 1, 1. So this is the fundamental condition which must hold so that we can use a simple min-cut max flow algorithm to find the global optimum in for our binary pairwise MRF. Let me write by a mere max flow min-cut. Much cheaper, of course, than the NP-hard general case. That can represent the energy. Exactly. So it's exactly like you say, it depends on the, again, this is a kind of smoothness assumption. So it says the energy of having label 0, 0 or label 1, 1. If you add these two energies up, they should be less than the penalties that you incur for a label change. And if you construct a model in this fashion, and this is what has become a huge sport in the past decade, because we have a cheap algorithm for this particular case. So models were hand designed and handcrafted for the submodularity condition to hold, so that the global optimum could be found very efficiently. You said it very nicely. Okay, now I mentioned these, actually we get here 3 conditions out and only one of them is fundamental. And I want to explain about the other ones. So using a more general graph construction than the one you've seen, there are different ways of decomposing this matrix of A, B, C, and D. One way, and I think that's the way shown in the paper by Kolmogorov and Sabi, is to say we have a constant term plus. Now I want matrices that depend on only the one or only the other variable. So I'm replicating here the first column, and then I'm replicating the first or the second row. And then I need one term to make everything come out nicely. So let's look at the upper left corner here. I have minus C plus A plus C, and I wanted to get out A. So I already have A and I don't need to have any correction term here. How about the term on the upper right? I have minus C plus A plus B, but I want to get out plus B. So I need a correction term here that is plus B, and then subtract all these wrong terms. So it's plus C minus A minus D. And then it turns out that here in the bottom left corner, minus C plus C plus C, that already gives me the desired C. I need no correction. And similarly, this one is already correct. So if you want, you can rewrite this in terms of, if I want to stress the fact that the first one is constant, I can rewrite it like this. The second one is the row matrix of ones, and the next term I can write as outer product of a column matrix of ones. And then I have this truly higher order term here, or not higher order. Anyway. And I can draw the associated graph. So source, Vi, Vj, and sink. Again, source corresponds to label 0, sink corresponds to label 1. And let's look at first at this function which depends only on I. So if I go back to this table where I introduced the abbreviations here, I said that the rows of the table are a function of xi, the columns of the table are a function of xj. So, in other words, this thing here is a function of xi only. And this is a function of xj. And if I scroll back once more to what we had done in the unary case, I assigned the potential of the node belonging to class 1 to the top arrow, and the potential of the node belonging to class 0 to the bottom arrow. And this is the same recipe that I'm using now. So this is why I'm getting a C here and then an A there. So these arrows together have represented this function of xi only. Now similarly, I can represent my function of xj only by having a D and a C. This is now the right side of this graph. The constant term here I'm not plotting at all. And now I'm left with this more complicated edge, which goes from I to j and has a capacity of b plus c minus a minus d. And we can now verify that all the cuts still give us the correct energy. So let's take, for example, this cut here. It gives me an energy of minus c, because this was the constant term that I have to always add, plus d plus b plus c minus a minus d. This comes from the second edge I cut through, plus an a from the third edge. So cancelling the a's and the d's and the c's, I'm left with b. And b was the penalty associated with having the first vertex in class 0 and the second vertex in class 1. Okay, just to confirm, I go back up to the table. B was having the first vertex in class 0 and the second vertex in class 1. And this is indeed the correct value that I get here. Okay, and you can similarly check that if you perform all 4 possible cuts, this graph here will always, if you take into account this additive offset that I mentioned, will always give you the correct energy. Now, how does this relate to the graph that we saw further up? The graph further up had only 3 edges. This one here. And let me say again what the values of these edges were. So we finally computed the edge k to have a capacity of c minus a. And we computed p to have a capacity of c minus d. And we computed m to be this more complicated thing, b plus c minus a minus d. So if you can now remember these for a moment. For example, look at the edge on the top left. Yeah, it has a capacity of c minus a. And this is what I can reduce the current graph to using the recipe for simplification of unary graphs. I can make the simplification if indeed c is minus a. So if c minus a is not negative. If that is the case, then I can delete this edge here and give the one up there a capacity of c minus a. And similarly, if c minus d is non-negative, then I can delete this edge here and give this one a capacity of c minus d. And now we have the graph that we saw earlier on. So this simple, I've been using this simple recipe from up here. So where I took a graph that originally had 2 edges and turned it into a graph with a single edge. And this works for this works only for terms involving one random variable. Now you are right in the sense that these matrices A, B, C, D, it turns out that I can always bring them in one of 2 normal forms. I can always express this as either 0, 0, and then some term, I don't know what to call these now, C1 and C2, if the problem was submodular. And I can always turn this into some other C3 and C4, 0, 0, if the problem was supermodular. This transformation is always possible. Okay, so here is one graph that I constructed, but it's still somehow asymmetrical, or it still was asymmetrical. Let me draw it again, because the middle edge is going in one direction and not in the other. And I want to understand this asymmetry better. And the decomposition that I showed here was not unique. So I can decompose differently by saying that A, B, C, D is now, so rather than replicating the first column, I can replicate the second column. And here I replicate not the first or not the second row, but the first row. So this would be AB, AB. Then I again need a constant term for correction, which in this case prevents overcounting the b's. You see I have b's in both unary terms, so to prevent overcounting I subtract them. And then finally I have this matrix with a single entry, which is as before, b plus c minus a minus d. and I can draw the associated graph. And it turns out that, again, I'm using the recipe for the unaries here, which says D goes to the upper vertex and B to the lower vertex, and here B goes on the upper edge and A goes on the lower edge. And now I have the vertex pointing in the other direction. And again, you can verify by taking all 4 cuts that this will give you the correct energy, provided that the submodularity condition holds. So again, all capacities must be non-negative, and this is true exactly if B plus C minus A minus D is larger than or not less than 0. So now I have 2 decompositions, and both are a little bit asymmetrical. And if you want, you can now take this decomposition, let me call it 1, this decomposition 2, and then you can add them up. So you can take 1/2 of decomposition 1 plus 1/2 of decomposition 2, which still gives you, of course, A, B, C, D. And that then results, so you also add up these graphs with the corresponding capacities multiplied by 1/2, and that finally gives you a it gives you a symmetric graph. However, this symmetric graph has more edges. So I'm just showing the graph without giving the actual capacities. And having more edges will mean that we potentially will find more augmenting paths, which is not something you want. So the algorithm will run slower. You would like to have the simplest possible graphs. And this is why, if the values A, B, C, and D fulfill certain conditions, you can always find simpler graphs, such as this one here, which only had 3 edges. But that relied on these extra 2 conditions here being true, so this one and that one. And if these conditions do not hold, but then you can construct alternative graphs which also only have fewer edges. So from this complete and symmetric graph, I can compute a couple of simplified graphs. So now we looked first at the single side terms, and then we made this construction for a single pair of adjacent vertices. And if we want to do it for an entire image, then we add up all these elementary graphs, or we add up the capacities of the edges. So for an entire image, the construction looks like this. I have source, I have a sink, and I have no idea what USB device it keeps finding here, because there's nothing plugged in. Must be something, I don't know. And here's a tiny image with 3 by 3 pixels. And we now have these edges. I'm only showing them in an undirected fashion now. Graph vertices. And both the source and the sink are now connected to each and every pixel, or not quite to each and every one if you compute these simplified graphs that I mentioned. But if you use a naive construction, then you will connect them all. Where the capacities of these edges to the source and sink reflect to what extent a pixel would like to be class 0 or class 1. This was the Uri construction I showed. And the connections between pixels, they implement the smoothness assumption. And we can now find a cut, such as, the minimum cut will of course depend on these capacities, but one possible cut would be this one here, which would leave my points labeled as belonging to either the source, if I give the source one color, and the sink, if I give the sink another color. And I can hence read out from this graph cut what label each single pixel should have. And again, if I have a binary pairwise MRF with only submodular interactions, this gives me the globally optimal result, which is not a mean feat. Yeah? So out of 2 to the power of n vertices in the hypercube, we find in polynomial time the single one that gives us lowest energy. That's pretty good and explains why this has been such an important contribution. Actually, similar constructions like the one we've seen are still possible for cubic rather than just pairwise or quadratic pseudo-Boolean functions with submodular potentials. And I have not mentioned yet how the augmenting paths are really found. You could use Ford-Fulkerson, but it would be much too slow for a normal image. So the code, which is now known as GraphCut and developed by Kolmogorov, it is a variant of Ford-Fulkerson that recycles augmenting paths. So I'm not going into detail, but I want to explain you in words what it does. You start growing a tree from both the source and the sink, and you keep extending these trees until they touch in some point, at which point you have found, or at which point in time you have found an augmenting path. And now you can push as much flow through this augmenting path as the edge capacities allow. And if you now look at the updated residual graph, then the 2 trees that you have constructed may have fallen apart into forests. So you have one forest associated with the source and another forest associated with the sink. So why is that? So let's look at a beautiful tree here. This is the sink. Of course, the trees live on a Cartesian grid, so they look different. Let's say this is where this tree made contact with another tree that started growing at the source. And I'm now pushing through this path all the flow that I possibly can, which means that along these edges I will obtain, or I may obtain along parts of these paths, 0 residual capacity. And this is why I now am left with a set of trees, a forest, one for the source side and one for the sink side. And the algorithm now tries to find for each of these poor orphans a parent. So a way is searched to try and connect these back to the source. So this one can perhaps connect to that one, and this one to that one, and maybe a way can be found to connect this one here. and then follows another growth phase and so on. And the worst case complexity of this algorithm is not so good, but on grid structured lattices, so let's say you have a grid of pixels, a Cartesian grid of pixels, this is extremely efficient. And I cannot stress enough the importance that this algorithm has had in the last decade. Just because we had a hammer, so we, the community, people tried hard and make everything look like a nail. So many problems were reformulated so as to be optimizable by this min-cut max flow on suitably constructed graphs. And beyond the situations in which it can find a global optimum, this can be used as a subroutine in approximate schemes. So approximate schemes are required in many instances where you have multiple labels, not in all, so there's one exception that I will still mention, but generally multi-label problems are NP-hard, and then you can use greedy heuristic schemes which, however, use a graph cut in every iteration, and these are very successful. I want to mention one case where, even though you have multiple labels, you can use GraphCut to find the global optimum, because everything we discussed previously was just for two labels. It was for binary MRFs. And here is Ishikawa's construction, also found during his PhD. It is shown here for only 4 vertices, so this is not an image, it's just 4 pixels arranged in a line, and each pixel can have, in this sketch, 3 different labels. But really you would probably, use more than 3 labels, only this is the smallest possible image that you could draw. And now he uses a special construction which has the following elements. We have these forward arrows that encode the data term. So these forward arrows tell me, let's say for this vertex here, disregarding what the neighbors do, where I should preferably cut. So I can choose the capacities of these forward edges such that the label is given which is in best agreement with the local data. But beyond that, I have the smoothness terms. And here, for example, where the final labels are 1, 2, 2, and 3 for the first, second, third, and fourth pixel, note that the cut goes through several of these smoothness arrows. So the gray arrows here, the gray arrows encode the smoothness assumption. And let's say if I wanted to make a transition directly, if I had a different cut, let's say my cut moves along here and then goes up there, then I have to pay a penalty here because I cross these edges, and another penalty there. And this can be used to express convex costs, such as if I plot label difference here. So I assume that the labels can be ordered or arranged in a linear fashion, and that my smoothness prior is a convex function over these ordered labels. So for example, if all of these gray arrows have the same capacity, then cutting one of these arrows gives me cost of 1, cutting 2 of them gives me cost of 2, cutting 3 of them gives me cost of 3, and so on. So I can encode such a potential which penalizes the absolute value of the label differences. However, if I had only these two kinds of arrows, I could still produce strange cuts. So for example, I could produce a cut which goes up here and then comes back down and does something else. And now I would no longer know at vertex number 4 which is truly the label. So usually I have the convention that my label is just the point below the cut. So this would be the label for the first vertex, for the second vertex, for the third vertex. And now for the fourth vertex, it could be here, or it could be, my graph is too short. Well, let me do a different example here. Now for the fourth vertex, my label could be here, or it could be there. So I have ambiguity. I want to disallow my graph cut making such loops. I want a unique label for each vertex. And this is achieved by these dotted arrows, because note that when we compute the capacity of a cut, we always only consider edges going from source to sink. So a pointed arrow, which goes in this direction or in that, adds nothing to my capacity because it's pointing in the wrong direction. But this one here is pointing in the right direction, from the source cluster to the sink cluster. Okay, this is my source cluster, and here is my sink cluster. And if I want to prohibit this kind of folding back, I have to give these dotted arrows extremely high capacities. So if I'm giving these dotted arrows infinite capacity, such a cut which loops back will incur infinite cost and hence will never be used. And this is, I think, a very clever construction that allows to solve such multi-label problems also with a graph cut, under the conditions that my labels can be arranged linearly and the smoothness prior is convex over these labels. My final plot of the code is how to use that in an image space, because the above example was only a line of 4 vertices. So let's say we want to perform a depth estimation. And these would be here the various depth levels or the various labels. And this number of depth labels is a discrete set. So really I have a discrete set of depths that I consider. And I have 2 spatial dimensions. So this is my spatial dimension, let's say x and y. And now I repeat this special construction. So I can put my source here, there, and then I'm connecting the source with each and every pixel, and I'm connecting the sink with each and every pixel. And then I fill this volume. So now I have one more dimension. Now I fill this volume with this special Ishikawa construction. And if I now obtain a cut, let's say, a cut like this, I can directly interpret it as a depth map. And this volume of my cut really directly reflects the depth that I've been estimating in this data. And the data cube itself, it can come either from a disparity estimation from 2 cameras, or it can come from some range sensor that does not give you a unique depth for each pixel, but a confidence for different depths, and so on. So this is a smart way how GraphCut can be used to globally optimize even a certain subclass of multi-label problems. Now, for the remaining problems for which this nice scheme does not work, we need approximate algorithms. And next week is the last week where I will discuss inference schemes for Markov random fields. I will next week tell you what to do with multi-label problems, or what to do with cases where the potentials are not submodular. And in the weeks after that, at least in the 2 weeks after that, we will return to more image-like things, so less optimization and more features. And I will then, so not next week, but afterwards, tell you what to do with how to construct interest point detectors and descriptors, and how these can be used to solve real-world problems. Thank you.